Hello students, let us take a stock of what we have learned in the previous lecture. Some of the theories we learned are the Gauss theorems, some of the Gauss laws, and Ampere law, which is del cross H is equal to J, and then also the Biot-Savart's law. In this lecture, let us continue with Faraday's law and go for Maxwell's equations. First, let us consider one of the theorems, that is a Polk theorem. So this in fact connects the surface integral to the line integral. To understand this, let us consider a closed surface that let me mark it as S, and let it be oriented smooth surface that is bounded by a simple closed and a smooth boundary, a curve C with positive orientation, here I mean towards up. If F vector is the field vector, then integral, that is the surface integral of del cross F into ds is equal to line integral of F into dl. So that means it basically relates a surface integral of a curve of the vector field to a line integral of the vector field around a boundary of the surface. Let us go for Faraday's law, which is a very interesting one, which is also known as law of electromagnetic induction. Electromagnetic, you see that, electromagnetic. Okay, so first let us consider this figure. In the figure you could see two arrow marks. So one is corresponding to the magnetic field and other one is corresponding to the electric field. So they are related. How they are related? Let us try to understand that based on the experiments conducted by Faraday and his observations. What I observed experimentally is that whenever there is a change in the magnetic flux linkage in a circuit, an EMF is induced in it. That means magnetic flux linkage causes EMF, that is current. The flow of current in the circuit will in turn produce magnetic field of its own. Later Lenz discovered that magnetic field so produced opposes the cause for it, that is change in the magnetic flux. Hence Lenz stated the induced EMF is in such a direction so as to oppose the change causing it. Based on the above observation, Faraday's law can be stated as the magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux through it, and direction of EMF opposes the flux change. So that means it is nothing but mathematically we can state E, which is nothing but the EMF, is equal to minus of d phi by dt. d phi by dt is rate of change of flux density and it opposes, that's why that negative sign. Okay, and let us consider that as equation 1. And if you now let us again go back to the figure. In the figure, if you are considering that this itself as just a surface, and I'm considering or just naming it as the capital S, and change in flux of the field B through the surface can be obtained by integrating dou B by dou T into ds. That is this one. dou B by dou T of ds over the entire surface S. So mathematically E, that is EMF, can also be stated as minus of surface integral dou B by dou T into ds. Okay, that equation is 2. But also change in flux over S means, that is here, change in flux over S means, that is in the surface, means there is a change in the flux linkage. So that change in the flux linkage d phi by dt can be written as surface integral of dou B by dou T into ds. Okay, so mathematically you can write that, and that let it be equation 3, and it is a magnetic parameter. Okay, if E, that is the electric field, by definition of line integral, EMF E can also be written as the integral of, there is a line integral of E into dl. That is the electric part. That is both the sides are electric, so that is electric parts, which we call it as equation 4. From 2 and 4 we can just write, because left hand sides are equal, so right hand sides can also be equal. So integral of E vector dl is equal to minus surface vector of surface integral of dou B by dou T into ds. So we got a equation by equating the EMF part, so which is equation 5. So we know that by Stokes theorem, by relating line integral to the surface integral, we can write the left hand side of equation 5 as the surface integral, which is left hand side is a line integral, as a surface integral of curl of E into ds. That let it be equation 6. Now from equation 5 and 6, again wherein the left hand sides are equal, so right hand sides could be equal, we have this equation just by equating. Okay, by rearranging we have, because both of them are surface integral on either side, so by rearranging we can have the surface integral of del cross E plus dou B by dou T into ds, that is equal to 0. That is this equation. So from the above equation we have two parts. One is the part that is within the bracket, and other one is ds. The product is equal to 0. So that means one of that should be 0, but ds cannot be 0. That means the part within the bracket, that is del cross E plus dou B by dou T, can be equal to 0. Again by rearranging that, we have del cross E is equal to minus dou B by dou T. So that means that is nothing but curl of E is equal to time derivative of B, which is nothing but another Maxwell equation, which is third Maxwell equation. So above equation is the point or differential form of Faraday's law, and one of the Maxwell's equations in the point form. Okay, now we are left with one more Maxwell's equation, that is Maxwell equation 4, which is also known as Maxwell-Ampere equation. Before proceeding there, we learn some of the definitions related to the electricity. That is, first let us see the current density, which you already know. J is nothing but I by A, basically it is I by A. If we can also define it in terms of charge density and the velocity of charges. That means if V is the velocity of the charge and rho V is the charge density, then the product of that is equal to the current density J, which you can also derive in fact in this form, wherein you can just see J is equal to I by A, which we already know. You could define there I as Q by T into L. So that means you have L there, and A, you keep it as it is, but then you just multiply and divide by L. Just multiply and divide it by L. So then you just rearrange it as Q by A L into L by T. Okay, that means Q by A L can be nothing but Q by V, that is the volume, and L by T is nothing but length per unit time, is nothing but the velocity. So charge by volume is nothing but the charge density. So we have J is equal to rho V V. After knowing the current density J, let us try to understand the equation of continuity, where is again interesting to know a circuit with capacitor, without capacitor, a time dependent and time independent of currents, etc. We are going to learn here. Okay, what we have learned from Amperes circuit law is that previously del cross H is equal to J. That is, curl of H is equal to J. Now consider a DC circuit here. So in the DC circuit, you have a battery, you have a resistor, and you have the flow of current in this direction. Okay, negative to positive is the flow of current. And now in this circuit, you just consider a closed surface in the red one, and wherein the current is going to enter. Current is going to enter here, and current is going to leave because it is continuous. Okay, so the charge flow inflow to the surface is equal to the charge outflow. That means del dot J is equal to 0. Okay, so then by taking the divergence on equation 1, in equation 1, we can write it as del dot, that's a divergent, into del cross H is equal to del dot J. So that in fact we can write it as del dot del cross H, the left hand side as it is, but from del H is nothing but 0. So in the previous circuit, that is this circuit, it is nothing but a DC circuit which was without a capacitor. Now let us introduce a capacitor to the same circuit, and we have the AC supply. So when we introduce the circuit with a capacitor, for example, and if we have the voltage that is not going to be a constant for for the domestic purpose, it is 50 Hz AC supply, the current will flow through the capacitor. That means the circuit I is not equal to 0. In the circuit, I is not equal to 0. Since the capacitor has an insulation gap between the conducting plates, the charge inflow into the surface is not equal to charge outflow. That means that in the previous one we have charge inflow is equal to charge outflow. But here the charge inflow, because there is a gap, there is, if I change the color, okay, if I change the color here, okay, now you see that is a capacitor. Is a capacitor means it is a plate, parallel metallic plate, but in between it is an insulator, so that means the circuit is having a break. So whatever is entered is not going to left. So that means the charge inflow into the surface is not equal to the charge outflow. That means del dot J, divergence of J, is not equal to 0. Okay, so unlike in the previous circuit. But then we know that del dot J is can be written as minus dou rho V by dou T. That means charge outflow is equal to reduction of charge within the surface. Okay, so that equation is nothing but we call it as equation of continuity. Now let us proceed to get the expression for displacement current density, that is this equation. How we are going to get? Let us consider the Amperes law. Remember this equation, del cross H is equal to J. Remember this, because this is what we are going to modify into Ampere Maxwell equation at the end of this derivation. Okay, let it be equation 1. Now it holds for a static condition, and that we have already explained in the previous definition. Okay, hence to apply that to the time varying condition, Maxwell modified the Ampere law to suit the time varying condition. Okay, now let us consider Maxwell equation 1, that is divergence of D is equal to rho V, charge density. Let that be equation 2. Differentiate that with respect to T, just mathematical operation. So del dot dou D by dou T is equal to dou rho V by dou T. So that means left hand side is nothing but rate of change of flux density, and right hand side is nothing but rate of change of charge density. Okay, let them be equal. From previous derivation by the equation of continuity, what we have is del dot J is equal to minus dou rho V by dou T. Let it be equation 4, and now substitute that equation 3 in equation 4. So that means you are going to replace the right hand side of equation 4. So right hand side will be replaced with the equation 3, that is nothing but minus del into dou D by dou T. Now rearranging the equation, we have del dot of J plus dou D by dou T is equal to 0. This is interesting. That means look at this equation 5. What we had previous for a static field, del dot J is equal to 0. Now what we have, it is not just del dot J is equal to 0, but there is one more term that is there, which is nothing but dou D by dou T. So that is nothing but the displacement current density, which is represented as JD. Okay, so now what is that we had? So for dou G, del dot J for the static field is corresponding to this circuit, and for the time varying condition we are having this circuit. Okay, from equation 5, that is where we got this correction factor, and this correction factor we are going to add it to the Amperes law. I told you in the very beginning in equation 1. This is equation 1. To remember, there is del cross H is equal to J, wherein J is not just J because it is, if this is there, it is in Amperes law, holds good for static condition, but we also have to have the equation for the time varying condition. That is why instead of just J in the equation we are going to have dou D by dou T. That is nothing but Maxwell equation 4, or which is also known as Maxwell-Ampere law. Hence we obtained all the Maxwell's 4 equations. Now let us go for a small definition of our displacement current. We know already displacement current density, but now this is displacement current, which is a very interesting phenomena you will understand at the end here. Okay, consider the capacitor in the circuit, and that means you know about a capacitor, and voltage passing through the capacitor can be defined as V is equal to V0 into e to the power j omega t. Okay, so that is a voltage. Then if we consider the electric flux density, then D is equal to epsilon E. That also we know. Both are the fundamental equation. And one more fundamental equation we know is the definition for the field, which is nothing but V by D. Okay, so with these ones, let us go further. So now these are equations 1, 2 and 3. Now let us substitute 3 in 2. That means we are going to get an expression for D in terms of epsilon V by D. And substituting 1 in 4, then we have again D can be written as, because we are going to just substitute for V in terms of V0 e to the power j omega t. Let it be equation 5. And from the previous derivation, we know displacement current density JD is equal to dou D by dou T. That is equation 6. And that you know in equation 6 it was JD on the left hand side, but JD is nothing but ID by A. So that A I am going to take it to the other side. So equation will be ID is equal to dou D by dou T into A. That is equation 7. And by taking equation the previous equations, we can write ID is equal to dou by dou T into epsilon by D small d into V0 e to the power j omega t into A. So just by rearranging that, what you have is ID is nothing but displacement current as equal to J into omega into epsilon A divided by D into V0 into e to the power j omega t. That is equation 9. So that is nothing but the displacement current. So displacement current here is defined as the correction factor in Maxwell equation that appears in time varying condition. That means in the presence of the capacitor. And okay, what do we by current? How do we define current? Current is nothing but rate of flow of charge. But in the case of displacement current, it does not describe any movement of charges. So that means it is But the thing is, it is associated with a magnetic field. It is not a moment of charge, but it is associated with a magnetic field. That is the speciality of displacement current. So the consequence of displacement current is that a circuit with a capacitor, there are two types of currents. Look at this. There are two types of current. One is the conduction current, which is of course the flow of charges, which is represented at IC here. And another one is displacement current, just we have derived the expression for ID. So IC is the current passing through the dielectric, which is 0 in the ideal case. Why it is 0? Because it is an insulator, is a dielectric and an insulator. And ID is the rate of change of electric field between the parallel plates. See, rate of change of electric field. So that means leading to a polarization, where in between the parallel plates in the dielectric medium. It possesses the property of being itself associated with a magnetic field. This is important. It is associated with the magnetic field. Okay, now let us just summarize all the Maxwell's equation in a single table, which I have already given in the notes also. You could see that, because it is one of the important table wherein you will get the information of all, and you have expressions and definitions and the figures in a single table. Just observe the table. First one is the Gauss law with the electric field. So wherein we have del dot D is equal to rho V, that is nothing but divergence of electric flux density is equal to charge density. Second one is Gauss law, and that is in the magnetic field. So that is del dot B is equal to 0. The statement is divergence of magnetic flux density is 0. Third one is Faraday's law. Faraday's law is nothing but curl of E is equal to minus dou B by dou T. So there is a connection between electric and magnetic. The statement is curl of electric field E is equal to time derivative of magnetic flux density. 4. Ampere-Maxwell law. There again is a curl of H is equal to J plus dou D plus dou D by dou T. And again you have, there is a magnetic field, magnetic parameter, J is a current parameter. Okay, so curl of magnetic field density, that is H, is the sum of conduction current density and displacement current density.